Hello guys, once again, welcome to our channel. So we're back and we will be discussing another method in order to solve a first order, first degree differential equation. Now looking back on the different formulas or different method given to us to solve a first order, first degree DA. So there will already 7 methods presented, but there are times wherein those methods are not actually enough to solve for the differential equation. Now, there are equations still may not be possible to solve in any of the method previously presented. What are they? We have the VSDA, homogeneous, exact, inexact, variable, integrable combination, linear, and Bernoulli. So, those methods are not enough. But the equation may be transformed into another equation by changing the variable to a form to form a DA of a type wherein we know how to solve, so which may be covered in any of the method that I mentioned. The given DA is in itself will suggest the transformation that's needed. Okay, for example, you are given a DA y prime equal to sine of xy. So if a checking is done now with all the methods given to us, so this cannot be solved by a VSDA or any other of the method. Now, the equation may look simpler if the sum of xy will be changed. So I have to let a w or any other dummy variable which can be a replacement of the x plus y. Okay? So dy dx is equal to, so my dy dx is equal to sine of x plus y. Okay? And I would let my w to be a replacement of the x plus y. So it looks simpler if this becomes sine of w only. So the w is equal to, if I'm going to take the differential of this equation, because there are still other expression that needs a replacement. Okay, so dw is equal to the dx plus the dy. Okay, so you have two options. It's either to change the dx in terms of w or to change the dy in terms of the w. Now, looking on the equation written in a differential form, my dy is equal to the product of sine of x plus y times the dx. So, if the dx will be changed, so it will be changed with two expressions involving a differential. Now, I think it would be simpler if I'll be substituting the dy instead of the dx. So, the dy from this equation, pwede na ko ilisan of dw minus the dx. Because if I'm going to change my dx and my dx be equal to dw minus dy, so there's still a sign function which is to be distributed. So, in order to avoid that one, I have to retain the presence of the sine w dx, and I have to change my dy, converting dy with dw minus dx, and that's equal to sine w dx. Okay? So, I have a dx term, I associate my dx term with the other dx term, and I remove dx by factoring, including the negative 1 factor. So I come up with 1 from the dx and plus the sine of w from my third term. Now, this is already a VSD upon transforming my equation. So as a VSD, I have to go with variable separation. So I have a dw over the 1 plus sine w. Then we have the next term which is the dx, and we have 0 at the right side, which is already integrable. So I can integrate my first term, dw over 1 plus sine w minus the integral of the dx. No problem with this. This is covered by a formula including the integral of 0. So we can arrive with a general solution. But there's a little problem with the first term. This is not integrable when it is given. So there are two ways to integrate this. You can have the the half angle substitution can be, or we can have an identity to work with our denominator to express this as a single trigo function by providing with the conjugate factor of the denominator. Multiplying the denominator with 1 minus sine of w can arrive with 1 minus sine squared. Now, to neutralize, I'm providing the same expression in the numerator side of my fraction. 1 minus sine of w, okay? This is now cosine squared. Okay, I can further simplify. Okay, 1 minus sine of w over cosine squared. There's an identity After dividing every term with the cosine squared, 1 over cosine squared is secant squared. Okay? And the ratio of sine over cosine is tangent. There is still one factor in the denominator which is a cosine function, or we can have the 1 over cosine w that is left, which is also a secant of w. Now, these two are actually covered with a standard integration formula. Like, if we integrate the secant squared u du form, then I can have the tangent w. The integral of a product of secant u tangent u du is also a secant u. And then we have the minus x from the integral of the dx, correct? And we have that equal to c. I can restore the variable here to arrive with our final answer. I can maybe group all the trigonometric terms, and x can be associated with the constant c. Okay, so here I have the final answer. I have the tangent of the x plus y minus the secant of the x plus y, which is equal to x plus c. Okay, so that's how to solve our problem number 1, which wherein initially we cannot solve this directly, but after transformation, so we were able to arrive with a dA, which is a variable separable differential equation. Now the secant is somewhat the same with the first. I have to remove the presence of the x minus y by substituting this with w, or maybe other letter you want to use. So the w is the difference of x and y. Okay. dw, if we have to take the differential, then that is dx minus dy. The given is actually dy equal to this whole expression times the dx. No? So the dx must be written because it is more complicated if I'm going to change my dx, no? Because there are still other factor to be multiplied to the replacement of my dx. So instead, I'll be working on my dy, replacing my dy with, the dx minus w. Okay, so I have to substitute, no? dy is equal to the given expression will multiply with the dx. So ako lang i-rewrite in a differential form. The dy can be, what is the replacement of my dy? dx minus dw, which is equal to the whole expression, okay, multiplied with the dx, no? So it's easy to multiply because this is just a single expression that is distributed. Dx again, plus 6x exponential w dx. Dx is becoming common, so we can eliminate. I can associate the w here, and then I'd notice that again my dA is a variable separable dE. So I can proceed with variable separation. Okay, now I want to remove the presence of exponential w by dividing with exponential w, then this is removed. X and dx, okay, they can be part of a first term, no? Of the first term. Now, dw over an exponential w is not integrable. So instead of dividing, I may multiply with the exponential of the negative w. Okay, so still, I arrive with the same result, and this is the exponential of minus w dw. So we can now proceed with the integral. So we have x dx. When I do the integration, that is integrable, and we have 3x squared. Kine, my u is the minus w, and my du minus is a negative dw. So this is lacking with minus 1, and a neutralizing factor will be provided. So this is now taking a form of exponential u du. So by integration, we have, and this is a negative term because of this, so minus exponential negative w, which is equal to c. And I can restore my variable, going back or replacing back my w with x minus y. Okay, now this negative can be distributed. Okay, so I can arrive with the final answer, which is 3x squared minus the exponential of y minus x. And that's equal to c. That as our answer. Okay, this is the last. Okay. What can we replace there? Or did you notice something that can be changed? Okay, bilangin eh. Take note of the presence of sine and cosine. If I have sine y, its differential is a cosine y dy, which is an expression that is present here. So the sine y can be changed to w, and this whole expression can be changed to a cosine y dy. Okay, now. substitute. Okay, so I obtain an equation which looks simpler. Okay, so we have 1 plus 3xw for this, dx minus x squared dw. Upon checking, this is linear in w. This is dw, this is x, so there is no term involving function in w with the dw. I have a w here which is raised to power 1 only. So this is linear in w. And as a guide, my standard form can be dw dx plus p sub x then times a w and a purely x function which can be placed on one side of my equation. Okay? So dw over dx, and this is divided with a minus x squared. Okay? So this is now the result na dw dx, it must be followed with a term containing a factor w which is kine. So I can reduce x and with the x squared. So we have 3 over x, negative, correct? So w, and this is a negative term which is transpose, and that is 1 over x squared. So right here, I can have the px, I can have the q sub x, correct? Okay. So we can proceed with the integrating factor. What is our integrating factor? It is the exponential of the integral of the p sub x dx. So we have the exponential and the p sub x is minus 3 over x dx. And by formula, this will take a form of a du over u or dx over x with minus 3 outside, please, before the integral sign, and that is the exponential of minus 3l in x. To simplify, because there's e and there's ln, I have to let this be 1 by expressing that as a power of x. Okay? EL in x is equal to this expression which is x to power of minus 3. Then, general solution can be taken. So, this is linear in w, so it's w with the if, which is equal to the integral of the q sub x, which is x to power minus 2, the if, which is x to power minus 3, and a dx, then plus c. This is taking a new expression, no? Their product, which is x to a power of negative 5, then a dx. Okay, I can bring this down to change the power to positive. That's my w. Integrate. So, we have sine y. Restoring also my w, my y, no? And my w is sine y, correct? Okay, so we have sine y over x cubed. And the integral of this is x to power minus 4 over negative 4. Correct? And it's this one. No? Then changing the power or the power to positive. No? So this is a negative 1 over 4x to the fourth power plus c. If I'm going to remove my denominator, I can multiply with the LC the 4x to the fourth power. So I have 4x sine y, correct? Plus 1, this is transpose, okay? And that's equal to 4c, which can be called as c. c, x to the fourth power, and this is now your answer. Okay, so that's all for the simple substitution, where the substitution can be made out from the given differential equation. Okay, so thank you for watching until the next video, no? So thank you for being with us and have a good day. Don't forget to subscribe, no, if you are new to the channel. Okay, bye-bye.